Today we want to talk in more detail about column questions and row questions. So we're going to look at a matrix and the reduced or echelon form of the matrix, and we're going to see what the pivots tell us. This today is going to be all about reading what the pivots tell us. So this is the linear algebra thing. You read the pivots. Consult the bones. That's what we do in this problem. We roll the bones and then we see what the bones are telling us. Consult the pivots is the linear algebra version of that. And I just had a new idea for a D&D character. All right, so I've given you a matrix and the reduced or echelon form of the matrix. In no context, we could just identify the pivots and we're kind of stuck. We could say certain things about the matrix, but we don't know if this is an augmented matrix or just a coefficient matrix. So let's remove all doubt by saying, consider the matrix A and the reduced row echelon form of A. Consider the matrix A and the reduced row echelon form of A. So I'm going to say A is this matrix, and we're going to stipulate that it is row equivalent to this reduced row echelon form. Notice I'm not putting an equal sign because these two matrices are not equal. They are, hopefully, row equivalent, but they are definitely not equal. So by saying it this way, I have not said that this is the augmented matrix of a linear system. So that rightmost column thing is right out the door. So note. Not the augmented matrix of a linear system. So since I'm giving this matrix a name, it is not the augmented matrix of a linear system. Typically, we're not going to give an augmented matrix a name like A, because an augmented matrix should involve a coefficient matrix and some constant vector to represent the matrix equation AX equals B. So if I just say, here's a matrix A, it is not the augmented matrix of a linear system. So let's take a look at the pivots of A. We see that A has a pivot in the first row, first column, the second row, second column, and the third row, fourth column. And one thing to note about the pivots are in A. A has these pivots. These are the pivot positions. Pivot positions belong to the matrix, not the reduced or echelon form. We don't want to say that the reduced or echelon form has these pivots. We say that A has the pivots. We say A has a pivot in every row. A does not have a pivot in every column. All right. So we want to be able to read the pivots. So we notice that A does not have a pivot in every column. So that's what we observe. In the column questions, we see that A does not have a pivot in each column. So this tells us some things about A. First, we note that the columns of A are not linearly independent. That's really messed up way to saying it, but I want that not have a pivot to not linear independence. But we could say that the columns of A are linearly dependent. So one thing to note is when I say A does not have a pivot in each column, I'm not going to say the reduced echelon form of A does not have a pivot in each column. If we say it that way, we are implying that we think that there are different pivots in the reduced echelon form than in the original matrix, and that's not the case. The reduced echelon form shows us where the pivots are, but those pivots are in the original matrix. So we say A does not have a pivot in each column. Don't say the RREF of A does not have a pivot in each column. You don't want to say the reduced echelon form of A does not have a pivot in each column. The pivots belong to the matrix. The pivot positions are in the matrix. We're just using the reduced echelon form to find out where they are. The pivots are fixed in the matrix. The reduced echelon form just shows us where they are. The reduced echelon form is just what we use to reveal them to us. So we observe that A does not have a pivot in each column. Here are the things that we can say about A. Linear independence is a column question. So we could say that the columns of A are linearly dependent. Note that we're not going to say A is linearly independent or linearly dependent. That doesn't make any sense. We don't say that a matrix all on its own is dependent or independent. Sets of vectors are dependent or independent. So we have to say the columns of A are linearly dependent. By saying the columns of A it's a set of vectors. So when we say the columns of A, that's a set of vectors. The columns of A is a set of vectors. Are a set of vectors, form a set of vectors, forms a set of vectors. Anyway, the columns of A, that's a set of vectors. A is a matrix and thus is not dependent or independent. A is a matrix. Dependence, independence is something that we apply to sets of vectors, not just singular matrices. Oh, I shouldn't say singular, not just a single matrix. So you have to talk about the columns of A when you want to talk about a set of vectors. If you want to just talk about A, then you just say A. When you say A, you specifically mean this matrix. So the columns of A are linearly dependent. If we want to throw A into a matrix equation, there's another thing I want to point out. The reduced echelon form will expose any dependence relations among the vectors or the columns of A. Let's say that the columns of A let's name the columns of A. Let's name the columns of A, A1, A2, A3, and A4. They always get very clever names. So columns of A are A1, A2, A3, and A4. So note, let's let A have these column names, A1, A2, A3, A4. The reduced echelon form shows us a dependence relation among the columns of A. So we can see by this third column, in that third column we have 5, -3. That shows us that A3 is 5 times A1 minus 3 times A2. So the non-pivot column shows us a dependence relation. In particular, A3 is 5 times A1 minus 3 times A2. So looking at this reduced echelon form, if I could ask the question, are the columns of A linearly independent? The answer would be no. A does not have a pivot in each column. Since A does not have a pivot in each column, the columns of A are linearly dependent. We can also observe from the reduced echelon form that A3 is a linear combination of A1 and A2. Therefore, the columns of A are linearly dependent. But the reason that we would even be doing this in the first place is that A does not have a pivot in each column. It should always come down to the pivots. Pivots, if you're looking at a matrix, the reduced echelon form of a matrix, you should always go for the pivots. So what this means, if the columns of a matrix are linearly dependent, that says that if AX equals B is consistent, so if the matrix equation AX equals B is consistent, then there are infinitely many solutions.
I have a question.
Yes.
Where is B here?
There is no B in the matrix yet. If I put this matrix in front of X and ask it to be equal to something, then we'll be looking at an augmented matrix. But if we put this A as a coefficient matrix, there will be many solutions if the equation is consistent. The things that we want to connect here, the ideas that we want to connect is linear independence and uniqueness of solutions. Linearly independent vectors, we get unique solutions. Unique solutions is tied to linear independence. If we have linearly independent vectors, then if we have solutions, we'll get one solution. If the vectors are, the columns of our matrix are linearly dependent, then if the equation is consistent, we will have many solutions. Linear independence leads to unique solutions. So what that means is that since we have non-pivot columns in the matrix A, then the solution set will have free variables. I guess the variables were free to begin with, but we should only start invoking things like free variables if we're talking about an equation. So, for example, if I gave you this matrix and the reduced echelon form, and I say, are the columns linearly dependent, you could not justify that by saying there are free variables. My response is going to be when a bunch of you inevitably do this, because experience has taught me about a third of you will just start invoking free variables at this point. My response is going to be variables in what equation? I've just given you a matrix. I haven't given you an equation.
Sorry, I'm a little confused. So the if part, it doesn't do anything with the matrix A that you give it to us. It's just another example.
No. If this is the coefficient matrix, and I say this matrix A, and I put it in the matrix equation A, this matrix times X equals B, then we'll end up with, so AX equals B. So we'll be looking at, we'll put this matrix A in an augmented matrix with some coefficient, some constant vector B. So let me do an example. Let me work one up real quick. That'll work out. Nothing is making AX equal B consistent. I didn't say AX equals B is consistent. I just said if AX equals B is consistent, then we will have many solutions because we will have a non-pivot column in the coefficient matrix. So let's suppose I wanted to solve an equation AX equals B where B is equal to 0, -3, -3. Now I'm going to make an augmented matrix. I'll make an augmented matrix. So that's going to be the matrix 1, 0, -2, 2, 1, 3, -3, -1, -3, -1, 0, 3, 5. Here's the matrix A. And now I'm going to make an augmented matrix with B. Now I'm looking at an augmented matrix. Now I care about a pivot in the rightmost column. And I need to find the reduced echelon form of this augmented matrix. Notice that I'm really concerned with what's going on in the last column. But in X, we see, since we have pivots in the first, second, and fourth columns, we are not going to have a pivot in the third column. That means X3 is going to be a free variable. So if I do the reduced echelon form of this matrix, I'm going to take the matrix I had, I'm going to insert a 0. Then at the end of the second row, I will insert a -3. At the end of the last row, I will insert a -3. So notice that the first 4 columns are just the reduced echelon form of A. And now I get the last column would correspond to the constants. So I get this matrix with a 6, -3. So since A was, since, so this is the augmented matrix of a consistent equation. And we can see that there are going to be many solutions because of this non-pivot column. X3 is a free variable. So if I make X1, this is going to correspond to X1, X2, X3, and X4. Free variables mean many solutions. Here are the column questions. So we're getting stuck in some details right now. A does not have a pivot in every column. So the columns of A are linearly dependent, and there will be many solutions. If there are any solutions, there will be many solutions. If we have a matrix that has a pivot in every column, then the columns of that matrix are linearly independent. And if the equation is consistent, there will be a unique solution. So here was a choice of B, and we ended up with a consistent equation, a consistent equation with many solutions.
Professor, I have a question.
Mm-hmm.
So for example, if A times the vector X equals 0, when we make it a matrix, it will be an augmented matrix.
No.
No?
When we make it a matrix, when you make the augmented matrix of the equation AX equals 0, we make the augmented equation matrix.
Okay. Okay.
How you phrased it was a little bit off.
Okay. Thank you.
I have a question.
Yeah.
So for the first one, because the A is not the augmented matrix, so we are not talking about any solution.
Correct.
Okay.
Until we started writing AX equals B, until we started using that matrix in an equation, there's no equation, there's no solution set. We're just, here's the matrix. It does not have a pivot in every column. So if we put it in an equation and there are solutions, then there will be many solutions. So this brings up another important point about linear independence, because here's another sticky point. I want to make sure that we keep using pivots in our explanations. So if you recall, the definition of linear independence says that the columns of a matrix, so let's just write this down again. The columns of A are linearly independent if and only if the homogeneous equation AX equals 0 has only the trivial solution. So the columns of A are linearly independent if and only if the homogeneous equation AX equals 0 has only the trivial solution. What we're saying is that the only solution to AX equals 0 is the 0 vector. So the column, if we want to negate this statement, if I want to rephrase this statement for linear dependence, we would say that the columns of A are linearly dependent if and only if the homogeneous equation AX equals 0 has at least one, has a non-trivial solution. That's the opposite of only. The thing that I want to point out here is that the homogeneous equation is always consistent. A times 0 will always equal 0. So the homogeneous equation is always consistent. So we can't negate this statement by saying, making a conclusion and by saying that the homogeneous equation is inconsistent. That can never be. The homogeneous equation is always consistent. A times 0 will always get 0. 0 is the trivial solution because it's the one that always works. So when we want to say something is linearly dependent, we would say the columns of A are linearly dependent if and only if the homogeneous equation has a non-trivial solution. If the columns of A are linearly independent, then that means there's a non-pivot column in A. That's where those non-trivial solutions come from. So remember that free variables correspond to non-pivot columns. Since the free variables correspond to non-pivot columns, it's the pivots that's giving us the information. So if I give you a set of vectors and I say, are these vectors linearly dependent? You don't just want to say the vectors are linearly dependent because there are free variables. I will say free variables to what? And then you'll say that the homogeneous equation has a non-trivial solution. And I will say, how do you know? And I will keep asking you questions until you say the matrix A has a non-pivot column. Because that's what told you. You need to, when you're trying to justify something, you need to say what you're trying to prove, and then why you know that thing. And in the case of a matrix, you will know that thing because there's a non-pivot column. A does not have a pivot in every column, therefore the columns of A are linearly dependent. That goes on to mean all kinds of other things. But the reason that you know is the non-pivot column. So let's look at a smaller example. Let's suppose that we have a matrix C, and the matrix C is going to be 5, 3, -1. Oh, I don't need it to be a determinant 1. So 2. We are looking at a matrix. And when we're looking at a matrix in linear algebra, we should start wondering, I wonder what the reducer echelon form is. So we plug this into our calculating machine, and we find that the reducer echelon form is 1, 0, 0, 1. So one question to think about is, how did I know that this is the reducer echelon form of this matrix without making any calculations? That's something to think about in the background while we point out the pivots. So we look at the reduced echelon form. C has a pivot in each column. Therefore, the columns of C are linearly independent. The columns of C are linearly independent since C has a pivot in each column. Linear independence is what we wanted to prove. Pivot in each column is how we know that thing. Note that I stopped right here. I said what is necessary and sufficient, and then you stop. You don't want to say more things. When you know you've made your point, you need to stop. If you keep talking after you've made your point, like I'm doing right now, what you're doing is indicating to your reader that you're not sure. And sometimes I refer to this as shotgunning. You're just trying to throw everything against the wall, and hopefully there's a correct answer in there. The problem with doing that is you're increasing the likelihood that you say something incorrect, that you say something that just directly contradicts through some, you just said something a little bit wrong, and now you've contradicted what you're trying to conclude. But at the very least, saying too much is an indication that you're not sure of yourself and you're just trying to say more. It's also referred to as painting the lily. The lily was already pretty. You don't need to dress it up. You're already done. You made your case. I like how every time this subject comes up, I demonstrate exactly what I'm telling you not to do. Once you've made your point, stop talking. Or writing. Also, on a side note, don't dress up your language. Say what you need to say. This is math. It's okay if you all write the same sentence. I would be 100% happy if everybody, as long as you didn't just copy and paste it. By the way, I can absolutely tell when you're copying and pasting, so knock it off. If everybody just independently wrote exactly this sentence, that would make me happy. I know this would be like an English teacher nightmare. It's like, oh, they're plagiarizing. But in math, 4 times 5 is 20. I'm not gonna say, oh, I asked them what 4 times 5 was. Everybody said 20. They must be plagiarizing. That would be crazy. I want you to write the same sentence. I want you to drop off any kind of extra language. Don't try to build things up. Be technical. If that's too much of an imposition on your desire to express yourself, you need to find another outlet for expressing yourself. Draw some pictures, you know.
This is the lesson we give everybody before audits and inspections.
My wife wanted to point out that this is the lesson that everybody gets before audits and inspections. And when you turn in a quiz, that's an audit or an inspection. I don't want to make sure that you know what you're supposed to know and that you can justify what you're supposed to justify. And saying too much indicates that you're not sure. And you want to sound sure. All right, let's pause the video here and come back and talk about row questions.